during the break. I typed up, I modified, I found this code of the web somewhere, gigs for gigs.org. Then I modified it a little bit so it looks like the code from the book. So I have, oh, okay, it is zooming in, good. I have my, try to, okay, so this is my function. It sleeps for a second and it prints this with the given parameter as an integer. And here I have a thread of pool of 10 threads. I make a new thread, I pass this value I, and each thread, as soon as they start running, they sleep, okay? And then they print this message and they terminate. And when I run this, compile and run, I get this. So it is 28057. I run it again without recompiling. 051. I mean, it's going to change a lot because, as I said, because they are sleeping for a second each one, okay? So they're not sleeping for a total of 10 seconds. They are sleeping in parallel, okay? They are sleeping in parallel. So it's going to take 1 second after 1 second to print these. And every time I run this, it's going to behave differently, right? So there's the difficulty of running multi-threaded code. You don't know the order of it. And let me try doing this. Before sleeping, I am printing it. Okay, let me maybe change it before sleep. Okay. And then after that, let me compile this and run. I got a bunch of warnings about converting from void pointer to integer, etc. That's okay. Any guesses what's going to happen? I will get the same randomness, but because I don't have the sleep, maybe the starting times will be more predictable. But again, it's going to be okay. So it started with 0. Again, it is 2, 1, 3, etc. These are before sleep. Then after that, who is going to wake up from their sleep the first? I don't know. Okay. It depends on the scheduler's decision. Before sleep, again, even the thread number 0 doesn't start immediately, okay? It started with thread number 1. But it's like 4, 5, 6 goes that way. Try it again. Oh, this one is 0, 1, 2, 3. Yeah. Out of luck, just luck, okay? It is in order they started. Do it again. Yeah, it is doing the same thing, but it doesn't have to, right? That's the difficulty with the multi-programming, multi-thread applications. Most of the time it behaves one way, but from time to time, it behaves differently, depending on what you're doing with the operating system. Let me do this. Let me go to this one. Let me load up some more stuff from the web. Okay, so I am kind of messing up with the memory to see what's happening. Let's see. Yeah, well, it is in order. But if I compile it again, compile it and run it, it is in order again. I mean, the starting, as I said, it doesn't have to be in order. And I showed you that it wasn't in order. Yeah, not that one, not that one. Yeah, see, this one is not in order. Anyways, okay, this course is not about systems programming. Okay, this is a topic of systems programming to see how the thread library is behaving. Okay, so you are responsible for learning about this thread library yourself or from the systems programming course. We are talking about how we implement such thread libraries and thread support from the operating system. Okay, good. By the way, I installed this Ubuntu application along with the Windows subsystem extension. It looks like it very much looks like a very nice Unix environment. Of course, it's not a Unix environment, but everything works, including my X window applications like this. See, X window applications work too. It's kind of a little bit small, but I think I can make it larger by playing with the fonts. I'm going to make it larger somehow. I don't know how. Maybe don't use Xterm, something else. Xterminal. Well, it has some options. I forgot what kind of options it has. Xedit. Do I have Xedit? Yeah, I have Xedit. I have Xclock. Yep, I have all those. So out of the box, it just works. I suggest it. Okay, let's go back. So implementing the threads, okay? Threads are implemented in two basic ways. You either implement the whole thread library in the user level. In this case, it is not a topic of operating systems, or you can implement it in the kernel level. And there is a hybrid approach. Okay, we will talk about it. So let's do this, okay? In the user space, implementing the threads in the user space, this is what happens. In the user space, you do all of your scheduling yourself without telling the operating system, okay? All the thread library is in the user space. When you make a new thread, this process makes the new thread. When you do the scheduling, the process itself does the scheduling and everything. So the kernel doesn't know that there is more than one thread inside this process. The kernel would think that there is a process and there is a single thread running, but in fact, you are sharing that thread with many threads inside your process. This is called implementing the threads in the user space. So the operating system doesn't know about your threads. As opposed to this, the other approach is operating system knows about your threads, and it knows that there are more than one threads available inside the process. And to make a new thread, you make a system call to the operating system. Give me a new thread, make me a new thread, or terminate this thread, or yield this thread. That's why in your kernel space, you have your thread table. Like the process table, of course, we have thread tables too. It's very much like process tables, and you have your thread tables. Okay, so these are two different extremes of implementing your thread support, either in the user space or in the kernel space. And of course, as usual, we are going to make lots of comparisons between them. Which one is a better one for what kind of purposes? And as always, our answer will not be this one is better than the other one. The answer will be it depends, okay? It depends on what you want to do, okay? It has some advantages and disadvantages, and etc. Now we are going to talk about that, okay? So this one is obviously doesn't need the operating system support. This one doesn't need the operating system support. That's why doesn't matter if your operating system supports multi-threading or not. it will work on any kind of operating system, right? So that's the advantage of it. The second advantage of implementing threads in the user space is when you switch from one thread to another one, okay, thread switching, when you switch from one thread to another one, there is no operating system involved, so there is no context switching at all, right? So you don't make any but when you yield remember this function yield, remember this function yield, right? When you yield the CPU, it's not a system call. The thread scheduler immediately switches from one thread to another one. Okay, so there is no operating system involved. There is no system call. So context switching is very light. You don't have to invalidate your cache or anything like that. It is so convenient. So it is fast. Okay, in terms of scheduling, in terms of switching one thread to another one. This one, okay, when this one say that I am yielding the CPU, it tells the operating system that I am yielding the CPU. So you have to make a new system call. System call means that you have to change the CPU mode from user mode to kernel mode, and you know how expensive it is, okay? It is not as expensive as switching from one process to another process because the other space stays the same, no cache invalidation and etc. But still, nevertheless, it is some kind of a context switching. So that's another advantage of user spaces, implementing the threads in user space. Another advantage would be this. If you implement your threads in the user space, then scheduling algorithm for specialized algorithms, specialized applications like the web service would be possible. Okay, you say that, remember this one? I know that is an application. This thread is the most important one, the dispatcher thread. These are important, but they are not as important as this one. Okay, so when I do the thread scheduling, I treat this differently. I say that that has the highest priority. Okay. Well, kernel wouldn't know about that thread, right? If I am doing the scheduling in the kernel, for kernel, these are all threads. These are all threads. Or maybe the only thing you can do about maybe increase the priority of one of them. Well, I like to do more than that because I know the structure of my multi-threaded application, and I like to write my own thread scheduler for this kind of application without using the kernel's thread scheduler. Another advantage of that would be another advantage of implementing your threads in the user space. So these are all nice advantages of user space threads. Okay. So for the user level threads, thread creation, destruction, scheduling done at the user level by your libraries. Okay, threading libraries. To create a thread, you must allocate the storage for stack, program counter, state, etc. You keep them in a thread table like a process table, but this time you are keeping them in your user space. Okay, when a thread yields the CPU blocks, the thread library saves everything in the thread table, and the thread scheduler, which runs in the user space again, maybe as another thread, is the highest priority one. And using the thread table, you load that data and save that data. These are user level threads. Okay, those are the efficiency gains. No system calls needed, which is a big advantage. No context switch, classical context switch. No copying data safety across protection boundary, okay? And no need to flush the hardware memory cache. These are all the advantage of staying in the same address space without letting the operating system know what's going on. Well, we like the operating system, but most of the time we like to keep it away from our business because going to it's like government, it's like government, right? You like the government, but if I'm going to do my job, my business with the help of the government all the time, that's going to be too expensive, too slow for the government and for myself too. Okay. From time to time, I need government's help, but most of the time, I like to do my business without any involvement of the government. Other advantages, again, allows each process to have its own customized scheduling algorithm, like I told you before, and it scales better than the kernel level threads. I can have as many threads as I like as long as my memory is enough. Okay, if you have your threads in the thread table and the kernel space, you need to have lots of kernel memory for that, and that might be a problem for some operating systems. Okay, these are the advantages of having user level threads. How about the disadvantages of user level threads? Okay, they are all, well, I mean, the most important one is this blocking system calls. Okay, blocking system calls is the main disadvantage, and let's see what it means. Let's go to one of our favorite multi-threaded applications, web or the word processor, right? The word processor. Let's say I have this word processor of 3 threads. Let's say I have implemented everything in the user space. So I am doing my scheduling and everything, okay? Everything is parallel. Let's say this thread is running. It needs to write some data to the disk. So this one asks the operating system, this one asks the operating system to write some data, and that's going to take some time, right? Operating system say that, okay, I'm going to block you because it will take some time. But the operating system doesn't know that there are 3 threads running in the same process. Operating system thinks that there is only a single process running. So the operating system is going to block the whole process, including the thread scheduling and everything. Okay, so that beats the whole purpose. I mean, the whole purpose of having multi-threaded application is for this application is to continue doing screen refreshing and keyboard handling at the same time while the system is busy writing the data, right? In this case, my whole application will be blocked and I don't get any advantages of having a multi-threaded application. That's the biggest disadvantage of implementing your threads in the user space without letting the operating system know about anything. Okay, that would be a very big problem. Blocking system calls. Okay. Page faults, well, and I'm not going to talk much about it. Maybe we'll come to that one. But this is something to do with the memory management, virtual memory. Okay. If one of the threads is not happy about the memory it uses, if the memory is not sufficient, then operating system needs to get more memory. But while it is doing that, it's going to block the whole process. That will be a bad problem. Another one is this inability to benefit from multiprocessor CPUs. This is my computer system. I have CPU 1, CPU 2, and 3. Okay. And there is this operating system on it. And this is my process. And inside my process, I have 3 threads going on. If the operating system doesn't know that there are 3 threads on it, okay, it cannot do this assignment. Do this one, do this one, and do this one. All the operating system thinks that there is a single thread going on inside the process. So it will assign only one CPU to this process. Even though I have more CPUs available, they won't be get utilized. So inability to benefit from multiprocessor CPUs. Okay. But then the last one is um, the kernel can't automatically grow per thread stacks. Remember, the memory is given by the kernel to us as a process. If I need more stack space for one of my threads, the operating system doesn't know about it. All the operating system knows that there is one stack space for the whole process. I can grow it or shrink it. So I can't get that help in terms of growing my stack for each thread. Okay, so all these problems are caused by, operating systems inability to help you in terms of assigning processors, scheduling other threads while one of them is busy, or giving you more resources. Okay, so these are the disadvantages of user level threads. So as usual, the advantages of user level threads become disadvantages of kernel level threads, and the disadvantages become their advantages, and we are going to see. We talked about this blocking system calls, page faults, and etc. Okay, so as opposed to user level threads, see, each thread is holding its own thread table. It holds its own scheduler inside it, and etc. The process table is common for the whole operating system. It's in the kernel space. But when I come to implementing the threads in the kernel space, then you have to keep your thread table in your kernel, and thread scheduling and the process scheduling becomes the tasks of kernel, not the user level. Okay, so kernel level threads, kernel manages a thread. To create, destroy a thread, the originating thread makes a kernel call. Okay, similar thread table but in the kernel, and it is often integrated with the process table because each process should have its own thread table. Okay, there is no global one thread table. Each process has an associated thread table. No problem with blocking system calls. If one of the threads is blocked, then the kernel can schedule another one. Of course, multi-CPU case can be handled very easily, but thread switching is expensive. So it needs a context switch. I mean, it is still definitely better than process switching, but it is more expensive than the user level threads. Okay, user level threads. Okay, so that's the idea of implementing user level threads and the kernel level threads. As I said before, even if your operating system doesn't know about multi-threading, using the appropriate libraries without telling much to the operating system, you can have your multi-threaded applications without the operating system support. But you might run into those kind of issues. Any questions? Okay, if there are no questions, then continue. Well, with the kernel level threads or the type of threads, when you fork, okay, when you do a process fork, some issue, what happens to the threads? Okay, a process has, let's say, 5 threads going on. When you fork, okay, the new process will have the same number of threads, but that needs to be addressed. Okay, that's maybe. How about the signals? How about other stuff? How about the files and etc.? These are some issues, and it depends. The solution depends on your design philosophy. Okay, some people said that why don't we find a common solution for each of those problems? What was the problem with the kernel level threads? Switching is expensive. What was the problem for the user level threads? Blocking system calls. Why don't we do something hybrid? This is what we mean. Both of them. There is kernel level thread support. There is a thread table in my kernel. Okay. There is a thread table in my kernel. And this kernel thinks that there are 2 threads happening inside this process, but in fact, this thread is shared by 3 different user level threads, and this thread is shared by 2 different threads. Okay, so that's what hybrid implementations are. So, well, when it's going to complicate the whole thing, you have to have a scheduler for the kernel threads, and you have to have a scheduler for the user space. Okay, both of them, uh, but but you will address to some degree the problems of both user space threads and the kernel level threads. Okay, nice solution maybe. Okay, so that's one solution, hybrid solution. Kernel is aware only the kernel level threads and schedules those. User level threads are multiplexed. So if this thread is blocked, then these 2 also blocked. But the rest of them, these 2, can go on. Why? Because they are connected to this kernel level thread. So with this blocking can still occur, okay, but it is less severe. At least some other part of the application can go on. Okay. Another solution is this: scheduler applications and activations. Some people don't like it, but it uses the up calls. I mean, this is our usually the operating system structure. This is our hardware, right? This is our operating system. This is process 1, process 2, and process 3, right? So process 1 runs all the time. Whenever it needs help, it asks the operating system. It asks the operating system to give data to do something. When the operating system makes that data ready, it unblocks this process, and this process continues, right? That's the way of the that's the definition of the rules. That's the rule of the game. Okay, the process goes to the operating system. When whatever is asked, I would come back and I would continue. Okay, that's the rule. But now we are changing it a little bit. We are changing it a little bit. Something that we are going to call up call. Okay, up calls. This is what we are going to do. Normally, a user program calls function in the kernel, operating system call, system call. Sometimes, though, the kernel calls a user level process to report an event. It's like while P2 is running, operating system say that something happened. While P3 is running, operating system say that something happened. Even though I didn't ask the operating system to do, even though I am not, even though I can continue, operating system is telling me that something is happening. It's giving me some information. That's called upcall. Okay. Some people don't like it. This shouldn't be the case. I asked the operating system to get me some data, and I will be blocked until then. And when the data is ready, and I will continue. This architecture says that no, while you are running, operating system can come to you and give you some information. Okay, so your application becomes more complicated because now you have to handle two things, your program and your operating system information. So how do we use this for the multi-threaded applications? Okay. So the thread creation and scheduling is done at the user level. So I'm going to take advantage of context switching. Okay. So I'm not going to let the kernel schedule the threads for me, and I am not going to make any kernel your operating system system calls. So that's the advantage. When a system call from the thread blocks, okay, that's the problem, right? As a thread, I ask some data from the operating system. Data is not ready. It has to be obtained from the network. So I am blocked. Well, in this case, kernel does an upcall to the thread manager. So what does that mean? If I am blocked, okay, operating system doesn't block me immediately. It lets me continue. It says that your data is not ready, but you can continue. But as a program, I schedule another thread. Other thread is continuing. When the data is ready, operating system makes an up call. Okay, scheduler activation. The thread manager marks that thread as blocked and starts running another thread. When a kernel interrupt occurs that's relevant to the thread, another up call is done to unblock it. So operating system doesn't block me. It says that the call that you made is going to block you, but I will let you continue. So my application is smart. I immediately myself as a scheduler, I immediately block that thread asking for data, and I schedule another thread. When the data is ready, operating system is going to make me another up call, and I will take that up call and data is ready. I can reschedule the originally blocked thread. That's called schedule activations. As you see, it is a little bit more work for you to write when you write multi-threaded applications because you have to handle unblocking calls, right? You have to handle unblocking calls. But it is better than blocking your whole process for a simple thread. Okay, that's called scheduler activations. So that's another okay, that's another way to find the solutions of the difference between the user level threads and the kernel level threads. Schedule activations. The first one is hybrid, then schedule activations. Okay. So for the pop-up threads, I will skip that one. It is in the book. If you like to read it, just read it. I don't have that kind of time to talk about that. But this is similar. The idea of it is similar. Okay, good. Any questions so far? There are no questions. I will start talking about this. Writing multi-threaded code is very different from, well, not much, but it is different from writing single-threaded code. Okay, just okay. Then I will continue. So it's kind of a topic of systems programming, but again, I mean this kind of data makes it more concrete for you to understand what the threading is and how we behave in multi-threaded applications. Okay, local variables and parameters. Well, parameters are local variables too. Do not cause any trouble because they are in the stack, right? For each thread, since they have their own stack, no problems. Okay, but variables that are global to a thread, but not global to the entire program, not global to the entire program are a problem. Okay, so global variables, if they are constant, no problem. If they are not, then I have to deal with it somehow. One solution is to prohibit local variables altogether. That's what we tell you, right? That's what we tell you when you write C++ programs or C programs. Don't use non-constant global variables, okay? Or another solution would be maybe each that should have its own global variable, kind of a solution, but that kind of gets ugly. Okay, so let me give you a few examples here using threads. Yeah, especially with the C programming, I mean, there are some functions, for example, str tokenize. Do you guys remember str talk? str tokenize? Do you guys remember how it works?
No.
Maybe other people remembers it. Anybody remembers how the str tokenize work?
You can
You
select the strings.
you give it a string, okay? You say that, okay, I'm going to give you a string. We are going to tokenize it. Every time I call you, you give me a new token out of that string. Okay? For example, I give you this threads are nice. I give you a str tokenize this string at the beginning. Okay, the first call. In the second call, it gives me this word threads. In the third call, it gives me R. In the fourth call, it gives me this word nice. It tokenizes it. So how does it remember? How does it remember the original string? It keeps it in a static variable, right? It keeps it in a static variable. Okay. So static variables, as you know, they are kind of global variables. Global variables are trouble. Why? Because if there are two threads, running a str talk at the same time, their static variables will interfere with each other, right? So that's not going to be good. So we don't like static variables in multi-threaded applications. Don't use static variables. Don't use global variables. Okay. So we try to write applications that use reentrant routines. What's a reentrant routine? Reentrant routine is a function that can be called many times by different threads, and they are still function properly. No problems. Okay. So write your code always keeping in mind that your code might be used in a multi-threaded application. Okay, don't use static variables, don't use globals. Okay, and let's look at this one. Many C libraries, we don't like them. Okay, many C libraries use it that way. I am going to, this local time, the function local time, okay, let me find the local times, C function, local time, find it, yeah. So the local time is this one, and there is local time R and local time S, and I'm going to show you that, okay? So converts a given time, okay, since something into a calendar time expressed in local time. The result is stored in static storage and pointer to that static storage is returned. So see what's saying? I give a time value, it converts it to some other type, whatever it is not important for us, okay? And it gives me a pointer to that new value in a static storage. Well, that's trouble for the multi-threaded applications. Okay, that's trouble for the multi-threaded application. So a pointer to a static internal object on success or null pointer. The structure may be shared between GM time, etc. Whatever. Okay. So the function local time may not be thread safe. I mean, you cannot use uh, this local time in a multi-threaded applications, but okay, local time R and local time S, they are different. Why? Because they say that if you are giving me this time t, you need to give me your memory to store the results. Local time R. Okay, so there is no internal static data involved. There is no internal static data involved. And let me show you this. Okay, time t, I get the time. And these are time of okay, local time tier. Well, okay, local time S. I give you both the time to be converted and the buffer that will hold the converted time. Okay, so the local time is not thread safe, but the R and S, which were introduced in C23 and C11. Okay, they are thread safe. So the difference is this one returns a pointer to an internal structure. Well, if I call this 2 times, okay, my static data will change and one thread will modify the other thread's data. But if I give you the input and I'm going to give you a pointer to your output, and this will be local time R. Okay, this will be a much better solution. Okay, what if you need global variables? Well, I mean, I mean, if you are using global variables, then you should be very careful. Okay, if you are using global variables, then you should be very careful. That doesn't mean that you should not use global variables, because global variables are a way to communicate between threads. Okay, let's say one thread is producing something, the other one is consuming it. So how am I going to communicate between those? So I will write to a global variable, and the other one reads the global variable. So that's a type of interprocess communication. And interprocess communication should be a valid thing, but we should be careful about it. So we must synchronize access, but that will come later. So that's called inter-process communication. Okay, good. I think I will stop at this point. And if you have any questions, I can take questions. Otherwise, I will stop and we'll continue next week. Are there any questions? Okay, so we are well into our discussion of processes and the threads. We introduced the idea of processes and later the threads. Then after this, we will talk about inter-process communication. How do we communicate data between threads and the processes? It's almost the same thing. And after that, we will talk about, of course, how do we schedule processes and threads? What kind of things we should look at? After that, we will finish off with the CPU abstraction, which is the processes. Then we will go to memory. Okay, that's it for this week. I'll see you next week then. Until then, bye.